In this video, I discuss about mixing height. Sometimes it is called mixing depth. Mixing height refers to the vertical distance from the Earth's surface to the top of the well-mixed atmospheric layer where turbulent mixing occurs. It varies throughout the day, typically lowest at night and highest during midday due to solar heating. If you compare this to figures, you can see that at night it is lowest. So this is the mixing height, and at the mid of the day you will see that this is the mixing height, and this is the highest. Mixing layer is the atmospheric layer itself where turbulent mixing occurs. It extends from ground up to the mixing height. So if you see this figure here, so this is the altitude, so this is the mixing height, and from ground to mixing height, this is the mixing layer. Basically, mixing height, mixing depth, mixing layer are same. Mixing layer can contain pollutant, moisture and heat, making it a critical factor in dispersion modeling. So here if we again try to differentiate between mixing height and mixing layer, then we can say that mixing height refers to the specific point or altitude making the top of the mixing layer. So this is the altitude point here, and this is the top of the mixing layer. So this is the mixing height. From 0, if it is say 1 kilometer, then it will be the 1 kilometer would be the mixing height, and mixing layer is the entire layer where mixing happens. So it is the entire layer here the mixing happened. This is also from 0 to 1 kilometer height area. So at this point of this video and from my earlier two videos, we know that atmospheric stability is important because it determines the ability of pollutant to disperse vertically into the atmosphere, and we can say that up to the unstable layer from the atmosphere of the atmosphere from the ground, that is up to the stable layer, or from where stable layer, in other words you can say from where the stable layer starts, is the mixing height. But this picture is incomplete, and why we will discuss here. So first you look at the figure. It is the temperature profile of an area and the air is dry. We kept consider air is dry to avoid confusion between moist adiabatic lapse rate and dry adiabatic lapse rate. So we use here dry adiabatic lapse rate. So if you carefully see the figure here, you can see that from ground level to 0.5 kilometer, the atmospheric temperature is decreases with increasing altitude. So this is unstable layer, and from 0.5 to 1.5 kilometer, this is stable layer, and from 1.5 kilometer to the above, it is neutral, because here the atmospheric lapse rate is as same as dry adiabatic lapse rate. So this is dry adiabatic lapse rate, that is 10 degree centigrade per kilometer. So here you can see that it is 20 and 25, so 5 degree centigrade in 0.5 kilometers. So this is the representation of dry adiabatic lapse rate. So if as per figure, it will think that the mixing height would be 0 to mixing height would be 0.5 kilometer, because from after that it is the stable layer. So this will check actually is it right or not. So here we already discussed that the layer of air up to from the ground to 0.5 is super adiabatic, that is environmental lapse rate is greater than the adiabatic lapse rate, and so it is unstable, and this portion is subadiabatic from 0.5 to 1 kilometer, as environmental lapse rate is less than the dry adiabatic lapse rate and labeled stable. And in case of layer above 0.1.5 kilometer is neutral because it has a lapse rate equal to the dry adiabatic lapse rate. Now, if we consider three parcels of air at level 1, 2 and 3 in this figure, and if for some reason one of these parcels starts to move up or down, its temperature will change by 10 degree centigrade per kilometer at dry adiabatic lapse rate. So assume the parcel, if the parcel has moved and at new altitude, maybe it's lower altitude or higher altitude, just is moved to new altitude. If the parcel is warmer than the surrounding air, it will be buoyant and will rise, and if it is colder than the surrounding, then it will be denser and will sink. So for parcel 1, if it starts move slightly upward, then as here the dry adiabatic lapse rate is less than the environmental lapse rate, so it making the air parcel will be warmer than the surrounding air, so the parcel will continue to rise. But how far up we will discuss in later. There, but before that, we'll just see what will happen for parcel at level 2. If parcel 2 starts to rise, it will find itself colder than the surrounding air because the dry adiabatic lapse rate is greater than the ambient lapse rate. So it will sink back to where it started from. But if it sinks below its initial level, it will again colder than the surrounding, and then the air then it will continue to sink to the ground level. And for parcel 3, if it will rise, then at a new altitude it will be okay with the new altitude because the lapse rate, environmental lapse rate and dry adiabatic lapse rate is same. But if it starts down, it will be warmer than the surrounding air and will rise back to its original position. Now we come to the parcel at level 1. So how far will parcel 1 will go? Now it will go up and up and up, rising as long as it is warmer than the ambient temperature, but at that point the ambient temperature and the parcel temperature will be same. So at the point of 1 kilometer it will rise, so then stop. If it went higher than 1 kilometer, then it would find itself colder than the surroundings, so it would sink back to 1 kilometer. So air from ground level to 1 kilometer will be actually experience turbulent mixing despite the stable lapse rate is found from 0.5 kilometer and above. So this would be from ground to 1 kilometer would be the mixing layer. I think it is clear. Now we will solve two problems. Problem 1 is if at 10 kilometer altitude temperature is 40 degrees centigrade minus 40 degrees centigrade, calculate the ambient ground temperature. So in troposphere, temperature decreases linearly with altitude. So in standard environmental condition, we can keep that environmental lapse rate is 6.5 degrees centigrade per kilometer. So at the ground level, so it is at the temperature of minus 40 degrees centigrade at 10. So we come down to ground level, that is 0, that is we have to use this per kilometer. If it is a change at 6.5 degrees centigrade per kilometer, then it will be 65 degrees centigrade, but the initial temperature is 40, so it will be 25 degree centigrade of the ground ambient temperature. So using this formula, and this is the result. Now problem 2, an aircraft flying at an altitude of 9 km draws fresh air at minus 40 degrees centigrade for cabin ventilation. If at fresh air is compressed to the pressure at sea level, would the air need to be heated or cooled to be delivered to the cabin at 20 degrees centigrade? So at 9 kilometer altitude, the fresh air temperature is minus 40 degrees centigrade. So it is compressed. So compressed means the temperature of the air will increase. So if it increase, that is we need not to taking care of the moist adiabatic lapse rate or saturated adiabatic lapse rate, because as it is warmer, so then the moisture will be there. Otherwise we have to think about the dew point, so need not to think about that. So and it need to be the sea level. So total 9 kilometer at the rate of dry adiabatic lapse rate, that is 10 degrees centigrade per kilometer. So to come down to sea level, it will be the air would be temperature would be 90 warm, it will be warmer due to compression. So temperature will be 90 degrees centigrade, and the initial temperature is minus 40. So the overall temperature of the fresh air, if we compress to the pressure at sea level, its temperature would be 50 degree centigrade. Now as we need to be delivered at 20 degrees centigrade, so it will be air conditioned, that is cooled for delivery to the cabin. Thank you for watching this video.